Well, thanks for joining me, everyone. And today I just wanted to walk through just what's new with digital twins as that relates to MapleSim. So to kick that off, thinking about digital twins with respect to MapleSim, because I'm sure a lot of you have heard this term digital twin before, and it can mean a wide range of things. But when we talk about digital twins with MapleSim, we're referring to something that's more of a physics-based digital twin. So traditionally, when people think about digital twins, they think of, you've got a machine already, we're pulling all sorts of sensor data from it, and we're using that to create a predictive model of how this machine's working. But with our software, being a physics-based system-level modeling software, we help create digital twins before the physical product is created. So we're trying to give you that functionality of design space exploration and a whole range of features. Our digital twins are intended to give you that sort of functionality earlier in the design process. And what you're seeing here are just some examples of different products that we've been able to do that for some customers. And as for MapleSim, it's been in development now for over 10 years. And over the last couple of years, we've really been trying to focus in on the ways that we can help machine designers and machine builders get new features into their products and get them out the door faster. So with that being said, we focused in on one aspect of that, which is called virtual commissioning. That's where you use a digital twin in order to test your control strategies against a virtual model before you have to build a physical prototype, put your control strategy code onto a PLC and do that testing. You can do some of that now before the prototype is even there. And that's going to help you iron out a lot of different control strategy bugs that often don't present themselves until you've got some physical machine in hand. We've also updated a variety of component libraries, and I'll talk to that soon. And we've optimized the handling of large models. So as you continue to layer in details of your models, you add different domains to what's going on, you add some hydraulics, these models are going to be handled a lot faster. And that just helps keep the momentum of your design process, helps keep that up. And in line with all of this is a really real recent development to continue with our improvements to the virtual commissioning workflow. We've added now an optional connector for B&R Automation Studio. So for any of you folks out there that are in the world of control design, you've got a variety of automations, software projects or products that you use for doing your control strategy design. And one of these that's very popular is from B&R. It's their Automation Studio software. And historically, what some folks have been doing to use virtual models to test some of their control strategies, they've been using this technology that's called functional mock-up units. And this is a way to take the dynamic model from a software like MapleSim to wrap it up in what's called an FMU and to bring it into one of these new, one of these new control automation softwares. With this new connector, however, we've taken it further than that. So not only are you going to be able to get a real-time result from testing your control code as you feed in different torque values and you get out sensor data to see what that's actually doing to your model, you can bring that in easier now. And you're also going to get this 3D visualization. So you can really do a wider range of control testing all from within Automation Studio. So that's really new, and that's something you should be keeping your eyes out for. Just a little more about virtual commissioning before I go into some more MapleSim 2018 features. This would just be a typical workflow to help wrap your mind around it. So let's say you've got some CAD data from a machine that you're designing. You can bring that data in to MapleSim. We have a CAD toolbox where you can just import that. We take all sorts of the most common CAD formats. And from there, you've got a variety now of rigid bodies with moments of inertia. And in MapleSim is where you actuate that and you bring it to life. So you can see below now, we've got these components that are the different bodies. But now we've added in joints and motors, and even we've specified a motion path for that. Once you've got an actuated model, you can do all sorts of testing from within MapleSim. But really, the virtual commissioning aspect is, again, to take that as an FMU and to start testing your control program against that. Of course, you're not going to find every single bug. You'll always need some amount of physical verification. But if you can take out even 25, 50% of those bugs, then not only is that going to save you time, but for a lot of machine builders, there can be a real risk to damaging a machine when you need to test stressors to your machine. So getting that in the virtual world is going to help save maybe the need to build extra prototypes. Again, so now once you've got the physical machine, as you see in the top right, you can do some more testing with the digital twin itself. So you might be doing some sort of testing to figure out, potential lifespans of components. But we have some folks actually who run a digital twin in parallel to the operation of the machine. And this can just serve as a matter of really just the best diagnostics tool you could conceive of. If the machine starts to slow down in any way, the digital twin has this understanding of how the physics are all mapping out in that machine. What that's going to mean is it's going to be able to tell you that perhaps some of the slowness is because there's some added frictions in a certain joint. But we can just change our control code to account for that. And you can really get more life out of your machines this way, or you can replace parts before they cause any sort of line shutdowns. So it's kind of a workflow there, and you can almost enter into this process at a couple different places. If you already had a machine developed, you could just build some CAD for that, and we could develop a digital twin after a machine's already built. So there's a few ways you can get virtual commissioning implemented. For MapleSim 2018, let's just go over a few things that we've added now. So with virtual commissioning in mind, now we've added a new application that it allows you to create those motion paths. So you've all got motion profiles and the kinds of duty cycles that you're hoping your machine can run. Within MapleSim now, there's a new app that allows you to define signals that are going to adhere to all the constraints you've got on your design. So, acceleration constraints. So within this app, you can create those things now easier than ever and feed them back into your model. We've added support for more CAD formats. So again, this is just going to cover a wider range, likely whatever major software you're using to do your CAD modeling in. This is going to import into MapleSim really easily. And our FMI import is improved again. So all of this is just a variety of little nooks and crannies that'll really ensure that you're not going to hit a roadblock when you're trying to build a digital twin for a machine that you're designing. Our component libraries, like I mentioned, we've expanded the scope of them, and that's our model on hydraulics library. For a lot of these machines, you'll likely have some sort of hydraulic piece in there if you've got any substantial loads to move around. And we've updated this library so that the accuracy of those models can be better than it ever used to. Same can be said for pneumatics. So specifically, I suppose, these are the thermal effects that really add up. They're going to have a lot to say about the lifespan of certain components or about the frictions that'll be induced. And on the topic of thermal, we've made updates to the Cybernet heat transfer library. And this is a great library for getting heat distribution and thermal effect understanding a lot earlier in the design process than you might typically be used to. We like to call this sort of coarse grain heat transfer effects, because while it doesn't offer the kind of granularity that, say, an FEA technique would, it does offer quite a lot of detail that you can use when you're in an earlier design phase, where it's still easy to sort of pivot some design choices, to work on some countermeasures. Typically, if you're putting in all the resources into an FEA approach for heat transfer, you might be further along where it's going to be a lot more money and time to make some design modifications. And lastly, from those bullets there, just to talk briefly about the way we handle large models. It really just means that for yourself, the amount of RAM required to simulate and to handle large models has been reduced. And while your machine might be able to handle large models in a past version of MapleSim, this is becoming more important as folks use different things like the MapleSim player If you're looking to deploy this model around team members in your organization to help them get some more insight into the design process, this will make different individuals' specifications of their computer, make that less of an issue. So you can just be assured that you can pass these models around, and you can even develop them further on your own computer with just a faster pace to it all. So with that being said, with some of the features that we've added and how digital twins fit in for that, I thought I'd just walk you folks through a really great example of a customer that we had in Italy, and how they were using some of this digital twin technology to not only size motors correctly for this machine they were building, but to bring that in and to do some control design with that in mind. So specifically, this was an injection molding machine, and they had two main goals in this project. One was to determine an accurate motor sizing for this new mold closing mechanism they were designing. And that was really important because the injection molding machine is in an industry that's really competitive. So if you can find any place to shave costs, shave off some cost without sacrificing performance, they sort of need to find those spaces to stay innovative. And they also needed to validate a control strategy for this, because inherent to this this new design was that if a misalignment happened at any point during the duty cycle, the risk to machine damage is going to be great. There'd be a lot of metal bending and a lot of irreversible damage. So the constraints were high for this kind of design, and they needed to find a way to step into this in a way that wasn't going to cost them a ton of money on physical prototypes. They could walk these things out the door with the high confidence that regardless of what environmental factor was thrown at this thing, that the controller would be able to keep those two mechanisms in alignment. And that was enough to bring them to MapleSim and to be in our automation studio and to use some of that workflow I talked to you about. So we'll just kind of step you through how that looks, because it's pretty cool how they were able to answer both of these questions using just some great system level modeling solution here. So first off is the MapleSim model itself. So they had this new mechanism with some new geometries, forces being applied in new ways, and they provided some details of that to us. And those are things like a motor speed profile, all the little bits and pieces to help us create this MapleSim model for them. So you can see what the model looks like here. You can see all the different parts of that. And MapleSim was able to provide it does these 3D visualizations so you can get a quick check that the mechanism itself is modeling what you intend. So this was created quickly for them. With the right skill set, we can create these models in days. We have customers who do the same. It doesn't always take the weeks or months it might to take another approach here. There's no sort of by hand derivation of the math involved. And if you take a look at the model itself, you can see that this isn't simply just a sort of spaghetti mess of signal flow blocks. This is, it's called acausal modeling. You're actually dragging in things like joints or spring dampers, and then on a parameter pane, you're just tweaking what those parameters are for each component. So at the end of a modeling, it ends up representing your physical system in a way that can't be said for some other modeling techniques like this. And then lastly, you have this model, but a model is only so good as it actually represents the physical machine you're trying to create. So they had a previous design that was similar to this, and it was really the fact that it was using an old motion profile. So they had some data of a mechanism like this moving, but in a way that was a sort of an old profile. So we modeled the old motion profile first, and then we were able to validate that this mechanism mapped to reality for that. And then from there, moving forward, we were able to test out this new motion profile. So what you're seeing here then are the results of that test. And you can see that there's a variety of loading and torque results there. And then we took that data, did a little processing to it, and we were able to show what you may have seen these before. These are it's like a speed versus torque chart. And the customer, they provided us with their sort of intended motor that they wanted to use. And the blue line on this chart is like a speed torque peak characteristic for that motor, which basically means if the actual requirements of every point in the duty cycle, that being the green line, if they fell outside of that blue region, that would mean that the requirements on the motor fell outside of what it's able to produce. And that is just a one-way ticket to machine damage. So we're able to show them that for this new motion profile, the intended duty cycle fell entirely within this new motor. And in a really healthy amount. This motor isn't oversized drastically. We're really using a really well-sized motor for this task. And then this steps into the second part of the project here, which was the virtual commissioning, the control strategy. And what they did was they wanted us to model this new mechanism, but doubled. And now you can start to get a sense of like what it is they're doing here. Those two green plates are to be closing. That's the mold itself, and that closes and opens. And then the two mechanisms here, once we validated the motion profile and the specific motor, we doubled that. And those two mechanisms are responsible for closing those plates. So you can see the MapleSim model above there, and we've now essentially just copied and pasted the better part of the first model you saw to create that dual mechanism. And then we've added this mold subsystem, which if you were to double click in that, it's only 5 components. It's a spring damper system, and we've thrown in a couple parameters to simulate the load that's placed on these the two closing mechanisms as the material itself starts to push back against the mechanism. And then we have the injection molding screw subsystem on your left. There's only a couple components in there too. So it's actually a fairly simple model, even though it can predict with great accuracy actually realistic results. For something you may not have known, what MapleSim does is it collects up all these physics-based equations and it simplifies them as much as possible in a symbolic sense before taking that into a numerical integration. And what this means for virtual commissioning specifically is that these models run incredibly fast. They're often able to run in real time when many other modeling programs are not able to. So this is it's a key feature. It means when you bring it into your automation software, you can get real-time results out of this. So you can test your controllers in a really realistic way. So this is the FMU I talked about that's going to be used within Automation Studio to test that control strategy. So you're seeing on the right the controller design within Automation Studio. And then you see here, this is a representation of a functional mockup unit. On the left is just a variety of motor inputs. It's the torque of the two different motors, and then a couple other parameters that the customer wanted to be able to modify just for their testing. And then on the right is a bunch of sensor information of where the position of different components are. And that was all we needed to bring that into Automation Studio. Now, in the course of our project with this customer, they built a physical prototype of this, but the real sticking point for them was, although they could build this prototype, they couldn't afford to test a whole variety of like stressor conditions for it, because that would just end up damaging the machine time over time. But having that physical prototype meant that we could do a quick realistic check. And what you can see here is we've got our 2 torque responses for the model in blue, and then below we have the actual real results. And if you take a look at that, you'll see that while they're not identical, they're very, very similar. And that was enough of a closeness of result that the customer was more than confident to move forward with testing the environmental conditions that might cause a misalignment, and know that those results are really going to map onto reality. And then finally, we arrive at testing the controller for being effective at controlling for, let's say if one of the 2 motors started to age, or if there was some more friction, there could be a whole bunch of reasons why one of these mechanisms might start to lag behind. And it was the controller's job to make sure that we wouldn't even get a millimeter of this misalignment. Just with all the rigid connections there would have been machine damage. And over time, that would just be a real risk to the company to put out something like this that is only going to survive months of usage rather than years. So in MapleSim, we just added a friction component onto one of the two mechanisms. And within Automation Studio, we could pass a parameter through to that and start playing around with the friction on one. And what you can see below here on the right is after a couple seconds of operation, we turned the controller off and on after we simulated some frictions. So the red line there is just to say, with the controller off, yep, this is an issue. The misalignment starts to increase, and there's where the machine damage is going to happen. But with the control strategy, after just a few fractions of a second, it's able to dial back the velocity of one of the mechanisms, reduce a bit of the input to one motor, and it pulled it right back to alignment in a matter of maybe 20% of a second. So that was exactly what the customer was hoping for. And especially since they knew that model was realistic, this was the sort of the keystone piece here that helped them be confident that everything was going to work. That's sort of the end of that story, but you can see in that how by having some physics-based digital twin ahead of time, there's a whole variety of ways that can plug into your design process to give you the confidence you need to move forward with it. So whether it be sizing your motor properly, or trying to understand what the effect of different environmental conditions will be, there's a whole variety of ways that having some physics-based model of your prototype, that allows you to do that sort of testing quicker, safer, and faster than before. So wrapping up, if any of this is interesting to you, but you're sitting back thinking, well, we don't use digital twins and we don't really even know how to get started with it. Here at MapleSoft, we have a team of engineers. Their job really is to help remove those barriers. Because really, once you get started with this, it's not as new or scary as it might look. But we've got a whole set of consulting services to help you get off the ground for your first project. So you can see here, whether that means you want direct help with creating a digital twin that you can just use for your future projects. We've got a whole variety of services that'll really help you get off the ground with this and help train you so that going forward, this is a skill set that you can bring internally and you can make use of for projects to come. So if it's something you're thinking about, we definitely recommend you get in touch.